All right. So right now we're chapter 30. We're chapter 30. So we are going to discuss how to find the magnetic field. So basically chapter 30, first part of it is magnetic. By the way, any noise is captured by the mic, so we have to be really careful. Okay? Magnetic field calculation. Okay, that's our objective for the coming two lectures. We want to find the magnetic field. You guys, please, in the back there, please. We have to be very quiet. We're recording this, okay? Anything will be picked up, please. Magnetic field calculation of what? Okay, we are right now starting to get into really more interesting things than the first half of this course. We have 4 weeks left, okay? We have 4 weeks left. 3 times 4, 12 plus 2, that's 14 lectures we have. 14 lectures left. We want to use them wisely. Magnetic field calculation. Magnetic field due to what? Due to what? Due to a current source. So the source of the magnetic field, is a current. What type of current? Alternating or constant? It has to be DC, direct current. So far, we will be only dealing with direct current, meaning that it's excited by a battery. It's the original source of the energy is a battery somewhere in the circuit. I'll give you an example. So the Biot-Savart law stated is like this. This is a review of what we've done last time. It's a constant, the magnetic field. Bar means a vector. B is a magnetic field. The unit is Tesla. Is a constant. The constant is the permeability. Mu naught is the permeability of free space. Permeability of free space is a constant. And we have here I dl. Okay, I dl. This is infinitesimal current element. I dl crossed with r. R is a unit vector divided by r squared or little r squared, either as long as we define it. This is called the Biot-Savart law, and I like to add a d here. Okay, which means that this is infinitesimal magnetic field due to an infinitesimal current. Okay, this is a very important relationship, or an important formula, an important formula for deriving the magnetic field. Now, as this stands, it makes no physical sense as it stands. What do you mean by that? There's no such thing as infinitesimal current like this. This is I dl stuck in space, because there has to be a DC current has to go through a closed loop, has to go through a loop. All right? For DC, it has to be closed. So the understanding is that we're not done yet. The understanding is that if we have this formula is with the understanding that I have a wire that is making or creating a closed loop. Okay? So I'm going to take a chunk of that wire here, this chunk, and I'm going to find the infinitesimal magnetic field due to that little thing. It's a very powerful concept. Very powerful concept. it means nothing infinitesimally, but collectively it means something you can measure in the lab. Okay? All right. Now, one will say, the next thing that will come to mind, I'm trying I try as much as possible to preempt your questions based on my experience as a student. The next thing that comes to mind is that a loop that has a current in it, where is the source of the energy? Well, we don't show it to you, but we come here somewhere and we put a voltage source. We sneak in behind the scene and we put a voltage source. Okay? Because without a battery, you cannot have a current in a loop. You need a battery. Doesn't have to be a fancy battery, but you need a battery here. All right, so now let us decipher what that means. There's a lot of, that expression is really loaded. There's a lot of information in it. The simplest thing is that I'm going to take a scenario where is the current is coming out of the board. Dot, it means coming out of the board, remember? And X means going into the board. Just like an arrow. You see the tip of the arrow, it means it's coming towards you. You see the back cross, it means that you're looking at the fins of the arrow. So if I have a current that is going out like that, what does that mean? IDL, it means it's an infinitesimal length with a direction. Infinitesimal length in the direction of the current, that's what IDL means. So where is dB evaluated? dB, or the infinitesimal magnetic field, is evaluated at an observation point. Is evaluated somewhere. Let's say here. That is an observation, OP, observation point. So DL is going out like this. R, I need to now connect my current source with the observation point. And R is the unit vector that is pointing from my infinitesimal element to my observation point. So this is R hat. It's a unit vector. And R, capital R, is the distance between my observation point and my current element. That's R. What else is there to decipher? That's all. I need to know IDL. It has a value, it has a direction, and I need to know R. So the rest is I need to perform the cross product, IDL cross. Some books, to differentiate multiplication with a cross, they put the cross in bold font, okay, thick font. So I need to know the plane. So IDL is going in that direction. So I need to first thing determine the plane that has the R and the IDL. So obviously that plane is, that plane is a plane like this, right? Because IDL is like that, R is like that. So this is the plane that contains IDL and R. You cross product, you take IL cross with R out, crossed with R, you get a vector that is pointing orthogonally to that plane that I just described. Okay? So if you're here, the cross product will be a vector in that direction. Orthogonal to the plane or to the line that connects the two. Okay? I know this is simple. Some of you had seen this before, but the most crucial thing in formulating the integral is to decipher each component, as we will see soon today. Yes, question? How do you know the field is not pointing this way or not? Because IDL. IDL is like that. Cross it with R. If you want to use the right-hand rule, this, cross with that, the finger is pointing in this direction. Now, what is this direction? If you were, look, if you were to center your coordinate system at this point, what will the cross product be pointing at? It will be pointing at the phi direction. That direction, the one that is orthogonal to the line that connects. And this is just to give us some feeling of what is happening. We haven't solved anything yet. The other thing, so that's one piece of information, or that is starting to give us a feel of what we need to do to find the field where at an observation point. So if I were to go for this particular line that is going this way to infinity, if I were to find the field right here, let's say at another observation point on the other side, well, we do the same thing, and I expect that first of all, that the field will be pointing again across through in the direction of a line that is orthogonal to the plane that connects the source and the observation point. So it will be pointing out like this, pointing in that direction. The magnitude depends on, not the cross product, the magnitude depends on what? On the distance between them. So if you are farther away, the magnitude will decrease, and we can depict that as a vector with a diminishing line length. Okay? So that's why if we keep doing this for each point in space, we find that if you are at a constant radius from the line source, you get a constant field. Where is it pointing? In the phi direction. Okay, we'll solve some problems completely to get a better understanding of how this expression, the one that I boxed, is the most critical expression. Okay, that's the most important expression. People actually spend a lifetime building codes that evaluate this expression. Okay, one can have a nice career just writing codes that evaluate that expression. All right. Next is that I'm going to take two examples, only two. But they are important examples. I solve these examples in a way different from the way the books does it. Okay? Otherwise, there's no point of me standing in front of you. I believe that the method that I use is easier, but it's up to you. If you like what I do, if you like what the book does, then you have two ways to do it. Okay? So the first example is that we have a current source. So I have a current source that is infinite. So we start with a physical problem and then we idealize it. Start with a physical problem and then we idealize it. What's the physical problem? The physical problem is I have a copper wire or some metallic wire. It's infinite. And it has a constant current that is going through it, I. Is that possible? I mean, if it's infinite, it has to come back to close the loop. Okay, so there's idealization. So in reality, I cannot have that. But you know what? I can get away with it. Remember, keep in mind, we are engineers. Okay? It's better to really keep that in your mind at the very beginning of your academic career. Engineer. That means you really have to quickly think of a practical scenario. And here's a practical scenario. So I have, if this cooperates, yeah, I have a wire here. So let's assume that, by the way, this is more than one wire. There's an outer sheet. This is like the coaxial. But let's assume there's no two wires here, no outer sheet. Let's assume just one copper line. I hold it like this. Well, I need a DC current, so I have to go and turn around and put a battery and come back. But I'm just showing you part of it, okay? And I'm standing right here, very close. That's a good idealization. So I will assume for the purpose of finding the magnetic field right here, then this is infinite. And how do we determine what I'm telling you makes sense or not? Don't believe me, there's no faith in engineering. Well, someone did it, went to the lab, and they found out, well, yeah, it makes a lot of sense. If you're here, this prediction that I will show you soon makes sense. But guess what? If I'm 10 meters away, breaks down. Why? Because this is no longer what? Infinite. Okay? So we know the practical problem. We idealize it. Why do we want to idealize it? To be able to have an analytic solution. Okay? We want to have an analytic solution. So this is the problem. I need the first thing, I put the schematic of the problem. Next, I will put a coordinate system here. I need a coordinate system, so I'm going to label this as Y and this as Z. This is infinite, so obviously as much as above the Z equals 0 point can be found below it. Okay, it's symmetric. So as much copper as you have above this point, you have the same as below it. Idealization number 2. I'm going to assume that the current is moving by itself. So in other words, there's nothing holding it. In other words, there's no copper. Okay? Again, you ask yourself, what I'm saying, does it make sense? No resistance, absolutely. Yeah, I'm going to assume J is flying in space, in free space. Look, at the end of the day, whether what I'm saying makes sense or not, you have to go to the lab, do the measurements, and validate what I'm saying. That's how we do engineering, by the way. Okay? So, all right. So I'm going to do that. The first thing I do is that I take an infinitesimal element along the line. Infinitesimal element. So this is my IDL. My IDL. IDL should have a vector. The vector is pointing. I can take it pointing up in the current direction. Okay? So I will write down what IDL is. IDL is I D Z Z hat. That's what IDL is. The next thing is that I need, or you need to ask me, where do you want to find the magnetic field? Where do you want to find it? Well, for this problem, I chose this coordinate system to make my life easy. So I want to find the magnetic field at a distance. Here I use a distance of, well, I'll label it in a second. I didn't yet. A distance away from this line. If I find the magnetic field here, is it the same as any point along this line? Yes. Why? Because it's infinite. Okay? Because it's infinite, so I'm going to take that dotted line. I'm going to take that dotted line. Okay? So this is my OP, observation point. So I have something that, okay. So I need, this is my observation point. Look, I'm following up the same template, the same thing I did here. I create a straight line between my IDL and my observation point. So I'm going to take the OP out because I need some space. So R hat will be the unit vector pointing in that direction. So this will be R hat. And R, that's our, box that we're trying to evaluate, capital R will be this distance, R here. So R will be this distance here squared. So it will be Z squared. I'm going to give myself some root, Z squared plus R or Y, either one, okay? I used here, if this is a fixed distance, so I don't have to use Y or R, I can use A. So A squared square root, okay? This is R. And, right? Now, we have to be careful to distinguish between the observation point and the source point. Very similar to what we did for the electrostatic potential. This is an observation point. This is where's my right here? My observation point will not have a primed coordinate. My source will have a primed coordinate. So that's why I give myself some space. I'm going to put Z prime here, or Z prime. Okay? So now, okay, we have a source and we have an observation point. So I have to use coordinates that distinguish between the two. So the source will always, my style is to have a primed coordinate. So at the end, when I finish the integration, I will end up with unprimed. You don't have to do what I'm doing, but that's my convention.
So should we have I dz prime z hat?
Absolutely, I can do that. Absolutely. This doesn't matter, you know why? Because they're the same. Okay, but all right. So now I want to find that vector r hat. This is where a very common mistake is made. R hat is a unit vector. So r hat is found by finding the direction in that direction, or a vector in that direction divided by the magnitude. So it will be minus z prime plus a, minus z prime z minus z prime z plus a y hat. Correct? Did I do it correctly? Yes? Keep me on track. Okay? So down and this way, right? So minus z prime plus a. I can use either y or r. You can work with cylindrical coordinates, that's fine, but I chose y. This is not complete. I have to divide it by the magnitude, this one. Z prime squared plus a squared. Okay, so look, this is my style. I like to write each component separately. I wrote the first one, wrote the second one, the third one. What else is there? I'm almost done, right? So let's see what text I need to do. I want to give myself some room here. So now I can write B. B is the integration of all of that. B is the integration mu naught divided by 4 pi integration of I dl cross R divided by R squared over entire line, entire current line. This is a qualitative picture of what we're doing. We have to substitute everything in. So I have mu naught divided by 4 pi integrating from minus infinity to infinity, right? Minus infinity to infinity. And I'm going to start putting everything else. So I can take the I out. I took the I out. I have dl, so I have dz prime z hat. Okay? Cross. Don't rush into these. you can easily make a mistake. Don't rush into it. Crossed with what we have right there, which is interesting. In the notes, I used R, but let's continue. So now you have 3 ways to do this problem. So I used Y here, so I'll stick to the Y. So I have A Y hat minus Z prime Z hat, okay, divided by A squared plus Z squared to the power 3 over 2. What I meant, because probably you haven't seen the notes, is that I can have AR here. Is everybody comfortable with what I just said? In other words, you can be working with cylindrical geometry, because this problem has cylindrical symmetry. Okay? So I could have written AR hat. Wouldn't change anything. Any problem with that? There shouldn't be any problem. Yes?
Why are the borders infinity and negative infinity?
Because the line is infinite, coming from minus infinity to plus infinity.
Oh, so we're finding the charge along any point on that.
There's no charge. It's a current.
Oh, so yeah.
Yeah. So the current is coming from minus infinity going to infinity. Okay? All right. So the hard part, this is part of the problem. The other part is to come up with a solution that will not make us spend the whole day solving for it. Okay? So I'll try to write here and give myself some space. So I'm going to squeeze this here. Z hat squared plus A to the power 2 to the power 3 over 2. And I'm going to take this out. You know, leave it in the notes. Don't take it out. But you know that we're integrating over the entire line. Just to give myself some space. So I have I mu naught divided by 4 pi. OK, so this is from minus infinity to infinity. Look at this. Z hat, I can cross it with Y hat. Z hat, cross it with Y hat. And then I cross Z hat with Z hat. Z hat crossed with Z hat is what? 0. Just remember, when you cross two products, you multiply their magnitudes and you multiply by the sign of the angle between them. So if the two vectors are collinear, what's the angle between them? 0. Okay? So I really don't need to cross this with this. Or if I cross it, I get 0. Some people don't like to solve this problem this way. Okay? That's why I'll just let you know, be comfortable that the problem that we're going to cover in this course are symmetric. Okay? If the problem is not symmetric, I'm going to ask you to write the expression and stop there. All right? If I were to take, look at this right here. Where? Right here. If I were to take IDL cross with R, where's IDL? There? Right? There. If I cross IDL with R, what will I get? Where will the direction be? Will one more time. You know, to cross two vectors that are far apart, you bring one next to the other one. It's the same thing. So I can move this here or move the R here. So I'd rather, just for convenience, I'll move this here. So I have IDL. If I cross it with this R hat, I will get a vector into the board, right? The right-hand rule. You have this here, this, cross, move it. Then you get a vector pointing inside. What's the direction of that vector? According to the XY system, X, Y, Z, it will be what? Minus X, correct? Minus X. But we don't have and. And what about the magnitude? I'm not writing it down because you'll see that in the book. I'm not using that system. What will be the magnitude of that product? I have to take this, multiply it by the magnitude of this. So IDL. What's the magnitude of IDL? Well, we took it out, no problem. I have DZ crossed with the magnitude of this. Multiplied by what? By the sine of the angle between them. That's a headache. Because that angle, look carefully, that angle, this angle, what's the angle between this vector when I bring it here, and this? It's this, right? Now imagine I am integrating over the entire line. Look, I'm integrating over the entire line. So my dz is going to change, which means that the angle is going to be changing. That's a headache. Look carefully, please. Look carefully at this solution in the notes and look carefully at the solution in the book. Okay? Here, what I did is that I spelled this out like that. And now I can take this, cross it with I, Z crossed with Y. What will you get? Z crossed with Y, you will get minus X hat. Right? It's an orthogonal X, Y, Z. Remember? X crossed with Y, crossed with Z. X crossed with Y will give you Z. Keep going. There's X here. So Z crossed with Y. Z crossed with Y will give you minus X. If you go backward, you have a minus sign. Okay? So I'll end up, I just need to worry about this. So what happened? I don't need to worry about the angle. Okay? So let's continue here. So this will be I mu naught divided by 4 pi I mu naught, this constant. I took it out, integrated from minus infinity to infinity. Remember, Z crossed with Z is gone, 0. So I have dz prime, Z crossed with Y is minus X. So I have a minus, I will take it out. And then I have X hat, right? And I missed a constant, A, correct? There's an A here. Divided by Z, all of this. All of this I keep it. Z prime squared plus A squared to the power 3 over 2. Now Mr. Newton will be comfortable because now this is something that he can recognize. This is calculus right now. Right? Before, that's not calculus. That's something that some of you might take in third level if you're interested in what they call it, forgot the name, not geometrical calculus, but vector calculus, thank you, vector calculus, okay? Vector calculus is one of those courses, if you take it with the right professor, you're in heaven. If you take it with the wrong one, you're doomed. Okay, there's no in between. Anyways, we've done some of this in this course, vector calculus, but without going too deep into it. All right, do you see? Now, the problem is becoming actually quite easy. Very simple. Why the problem becomes very simple? Because we can look up an integration table. That's why it becomes quite simple. And we can do that. You see, the integration, remember, the integration variable is here, is inside the integral. Right? And I'm integrating from what? Z prime equals minus infinity to Z prime. Right? This is dz prime. And why, you see, now you would appreciate why we differentiate the two. Guys, please listen to this. Gents, please. That's why I strictly keep saying we should differentiate between the two. because the integration is over the primed coordinates, right? The integration over the primed coordinates. Why? Because I'm integrating over the source, right? All right, so the answer, you look up the table, and we find minus mu naught I divided by 4 pi x, and we have here r being this distance a, okay? So I can leave it actually as a, it's okay. And then I'll change it in a second. This is the magnetic field. So I solve for this problem. I can generalize this problem. I can generalize it. So if you ask me, what about if I am at same distance but in this direction here towards you? The solution should be the same, except for the direction, correct? In other words, if I am a meters away towards you, how will the solution be? It will be the same, except the vector will be pointing in which direction? In the y. So in general, where would the vector be pointing? In cylindrical coordinates phi. Okay? These are the kind of questions that you might see in the final exam. In other words, you solve the problem, and then I ask you what seems to be a tricky question, okay, but it's not tricky. Just want to make sure that you understand your solution. That's all. All right. So I'll put the final answer here. Okay. So what I've written there, what I've written there is absolutely correct. But if I want to generalize it to any point, okay, to any point in space, B will be mu naught I divided by 4 pi r, where r is the distance between the observation point and the line, and the direction will be phi hat. Okay? So this is generalizing it to any point, any observation point in space. What are the constraints, or what are the conditions? What are the conditions that we are bound by to have this solution? What are the conditions? What are they? Yes, anyone?
I guess your chart figure source has to be infinitely long.
That's all. As simple as that. Now, remember, I gave you that example, so it has validity within reason. It has validity within reason. Okay. What happens now? You see where I'm heading. Before I give you a feel of what is happening here, let's have a quick example. A quick example. I have a material with a resistivity of 1.1 times 10 to the minus 6 ohm meter. This is the resistivity of a wire. So it's a 1 meter wire. 1 meter wire, so it's exactly 1 meter from here to here, is connected to a 20-volt battery. So look what I'm doing. I am going to connect it to a 20-volt battery. So I don't show you all of this business. This is not shown to you, but this is what is connected to it, 20 volt. The diameter of the wire here, this is D, is 0.001 meter. I gave you the resistivity of the wire, the diameter of the wire, and I want you to find the magnetic field strength. Find B at 1 meter away. Find B 1 meter away. Okay? So the first thing is to find the current. So I need to find I in this wire. I is, using Ohm's law, the voltage divided by the resistance. So the voltage divided by the resistance. The voltage is 20. The resistance is, we learned it before the before the reading week, rho L divided by A. Resistivity multiplied by the length divided by the cross section. So this is the resistance that depends on the resistivity. Okay? So I, which turns out to be, if we do all the math, it will turns out to be 14.3 amp. Okay, 14.3 amps. That's very, very high current. Very high current. In reality, I know you guys are going to get back at me and you will say, what an example. I thought we were engineers. Yes, if you get a battery, which is 20 volt, a good battery, let's say a car battery, and you connect it to a wire like this, what will happen? It will start dying soon. Okay? Because the resistance is, well, for this one, if you do the math, the resistance is 1.4 ohm. So practically you're shorting it. If you're shorting it, that's why you get this huge spike. So when you get this huge spike, what you're doing is that you're drawing a lot of current from the battery. You draw a lot of current, which means that the power that is being kicked out of the battery with time is increasing, and then it says, oh, I can't deliver any more power. So this model breaks down. Someone had a question, yes?
How long is it piece of wire?
How long? 1 meter. Yeah, I lumped all the math right here. I gave you all the relevant information, the resistivity, which goes here, the length is 1 meter, and the A depends on the cross-section. The example is in the notes. Just to give you a feel of what, what numbers we will have. So I end up with B, the magnitude of B. We put all the numbers into the final answer, which is right here. For 1 meter away, B will be 2.6 or 2.86 times 10 to the minus 6 Tesla. Okay? Is that high or low? This is a practical example. This is on the lower side. Okay? This is on the lower side. MRI machines are rated by the Tesla. 3 Tesla, 1.2 Tesla. 1 Tesla is a huge magnetic field, very, very high magnetic field. So this is obviously is on the lower side. Any questions? This is physics, right here. Okay? The rest is physics, geometry, calculus. Really. Physics. In other words, if the apple fell on Newton's head or did not, that he would have never come up with this. Okay? This is completely different physics from the gravitational thing. This is physics. This is the Biot-Savart law. Geometry, you really need to be very careful about the geometry. And finally, you are here. If you cannot go beyond this point, I'm not too worried. Okay? Because the idea is to have a table. Just hold on 1 second. The idea is to have a table. Before we break, what happens if this is not infinite? What happens if this is not infinite? A, we panic. No. Tell me, guys. Yes, please. What's that? Okay. So if this is not infinite, I have to integrate between finite values. There's no harm in that. Okay? No harm in that. That's when we use the computer. But the computer cannot figure this out. The computer doesn't do geometry. Right? Because the computer does addition, subtraction, multiplication. It doesn't do the geometry, the computer. So don't think that they're really smart to do geometry. It doesn't. This one is what? It's just simple addition. Okay? So I can simplify certain problems. So if this is finite, if I were to ask you let's say there's a B above and a B below, and if I ask you to find the point there, it might be doable, actually, analytically. But hold on. But if I were to ask you, find the field right here, right here, and if the line is infinite, how complex would this problem be? Same. Exactly. Exactly. Just wanted to see you. If it's not infinite, it's difficult. Analytically, not difficult to express it. Do you see that? In other words, you don't have an excuse. Don't tell me that we cannot solve problems that are finite if I ask you express it like this and stop. You can do that. Express it and stop. Okay? To complete it is a different story. Okay. All right, we'll finish. We're finishing 2 minutes early today, so we'll make up for it next time. Okay, thank you guys. See you this Wednesday.